Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends. In this video, we will study the measurement of frequency using the Weins Bridge. Here we will study first the circuit diagram of the Weins Bridge, then we will derive the balance equation and see that how frequency can be calculated by this bridge, and also we will study the phasor diagram for this Weins Bridge. So let us start with our topic. Weins Bridge is used for the measurement of frequency in the range from 100 Hz to 100 kHz. And the accuracy of the Weins Bridge is from 0.1% to 0.5%. It is called Weins Bridge after the name of the scientist who invented it. So it is called Weins. The name of the scientist is also Weins. Now, Weins Bridge, it is a type of an alternating current bridge. So it is consists of 4 arms having 4 impedances in it, and these impedances can be a capacitor, resistor or an inductor. These are the 4 arms. In these arms we are having the impedances Z1, Z2, Z3 and Z4, and these impedances, they can be a capacitor, resistor or an inductor, or a combination of these 3, series combination or parallel combination. Now out of these 4, Z1 is the unknown impedance which we want to measure. Now here we are measuring the frequency. So frequency is associated with the capacitor also and with the inductor also. So here our unknown impedance will be a capacitor, and the known impedances, they will be a combination of a capacitor or a resistor. So how in a resonance circuit we measure the frequency, here also we are going to measure the frequency with the help of this bridge. Now in this bridge we are having a detector also, which is used to obtain the balance of the bridge, and when the detector, it obtain the balance by indicating us the null deflection. When the indicator gives or when this detector gives us the null deflection, it means the alternating current bridge is balanced. Also we are having an AC voltage source which provides the power supply to the bridge network. So we will have these 3 components in the bridge network. Now let us see the circuit diagram for this Weins bridge and then derive the balance equation for it. So this is the circuit diagram for the Weins bridge. In this bridge you can see we are having the four arms AB, BC, CD and DA. In the arm AB, we are having a parallel combination of a capacitor and a resistor. In arm BC, we are having a resistor. In CD also, we are having a non-inductive resistance. And in the arm AD, we are having a series combination of a resistor and a capacitor. Now, in between the resistor R1 and R2, we are having a mechanical coupling. This is the mechanical coupling. Okay, and B and D points we are having the detector which is used to obtain the null condition, and this is the AC voltage source which is providing the EMF E to this bridge network. Now E1 is the voltage drop across the arm AB, E3 is the voltage drop across BC, then we are having E4 and E2 at the respective arms, and in these arms we are having the current I1, I2, I3 and I4. So this was the complete network or the circuit diagram of the Weins bridge. Now let us see how the impedances in these arms they can be represented. In the arm AB we are having the parallel combination. So the capacitance C1 and resistance R1 they are connected in parallel with each other. So when we are having a capacitor and a resistor in parallel, their equivalent impedance can be calculated. It is R, it is C. So 1 by Z will be equal to 1 by R plus 1 by XC. XC is the capacitive reactance. So XC value is equals to 1 upon J omega C. So here we can calculate 1 by Z equals to 1 by R plus it is 1 by XC. So 1 by XC will be equal to J omega C. Okay, so 1 by Z is equals to 1 plus J omega C R upon R, or we can say Z is equals to R upon 1 plus J omega C R. So here we are having capacitance C1 and R1 which are connected in parallel. So our impedance Z1 will be equal to R1 upon 1 plus J omega C1 R1. Okay. Next we are having the arm BC. So the impedance Z3 will be equals to the resistance R3 only. Next we are having the arm CD. In the arm CD we are having again the known non-inductive resistance R4. So Z4 will be equal to R4. Then we are having the arm AD or DA. So in this we are having the series combination of R2 and C2. So in series combination the Z will be equal to R plus XC, and XC is what? 1 upon J omega C. So here we will have the Z2 as R2 plus 1 upon J omega C2. Okay, so we have the value of the Z1, Z2, Z3 and Z4. Now when the bridge is balanced, then for a balanced alternating current bridge we have the balance equation which is Z1, Z4 equals to Z2, Z3. This is the generalized balance equation for an alternating current bridge, and this equation says that the product of the impedances which are present in the opposite arms, their product is equal to the product of the impedances in the opposite pair of arms. Okay, so here Z1 and Z4 they are present in the opposite arms, and Z2 and Z3 they are present in the opposite arms, so their products are equal. Now we have got the value of the impedances, so we are going to put the value of these impedances in this equation, and then we can calculate the unknown impedance Z1. Now Z1 is what? The parallel combination, that is R1 upon 1 plus j omega C1 R1. Z4 was R4. Z2 was the series combination, so R2 plus 1 upon j omega C2, and Z3 is what? R3. Now multiplying this and simplifying this equation, we will get R4 upon R3 is equals to, if we simplify this, it will be 1 plus j omega C2 R2 upon j omega C2. Okay, and this will be cross multiplied. The denominator will become numerator, so it will be 1 plus j omega C1 R1 divided by R1. Okay, again multiply this, we will get R4 upon R3 is equals to, multiplying this we will get 1 plus j omega C1 R1 plus j omega C2 R2 plus j square omega square C2 R2 C1 R1 upon j omega C2 R1. Okay, now here if we equate the real parts and the imaginary parts, it will be like R4 upon R3 is equals to, this is 1, if we take each term, then this will be 1 upon j omega C2 R1 plus j omega C1 R1 upon j omega C2 R1. So j omega and j omega, it will be cancelled. We are left with C1 R1 upon C2 R1. Then we are having j omega C2 R2 upon j omega C2 R1. So C2 R2 upon C2 R1. R1 and R1 cancelled, C2 and C2 cancelled. Next we are having j square omega square, and here we are having j omega, so we are left with only j omega. C2 cancel, R1 and R1 cancel, so we are left with R2 C1. Now here equating the real and the imaginary parts. Real parts are those parts which are not having the j omega term in it, so R4 upon R3 on the left hand side, it will be equal to, on the right hand side we are having these two terms in which no j omega is present, so C1 upon C2 plus R2 upon R1. This equation we have got. This equation was obtained by equating the real parts. Now equating the imaginary parts, we are having 1 upon j omega C2 R1 plus j omega R2 C1 equals to 1. So if we bring it to the other side, then we will get this 1 by j, it can be written as minus j, and this is plus j omega R2 C1. Sorry, it's equal to 0. Now from here, bringing the j as common, so it will be cancelled. So we are left with omega C2 R1 minus here plus omega R2 C1 equals to 0. Okay, so from this equation we will get omega is equals to 1 upon under root of R1 R2 C1 C2. Okay, so omega is the frequency, and we have measured the frequency by this Weins bridge. We have equated the impedances Z1 Z4 equals to Z2 Z3, and when we are simplifying we are getting these two equations. This is our first equation, this is our second equation. Now this is our angular frequency. Omega is the angular frequency. So if we want to measure the frequency F, so F is equals to 1 upon 2 pi under root of R1 R2 C1 C2 Hertz. When we are measuring the angular frequency, then our unit is radians per second. And when we are measuring the frequency, then its unit is in hertz. So we can measure the frequency also from this angular frequency. Now in most of the Weins bridge there is a mechanical coupling, as I have said. In the circuit diagram we have seen that R1 and R2 we are having a mechanical coupling between them. So through this mechanical coupling we can make the value of R1 and R2 equal to each other. Okay, so if we take this condition, R1 is equals to R2 equals to R, and C1 is equals to C2 equals to C. So this frequency term, it will now become F is equals to 1 upon 2 pi, because R1 R2 they can be replaced as R, so it will be R square C square. So bringing it out of the under root, it will become 1 upon 2 pi RC. And its unit is hertz. Hertz, or this is represented as Hz. So this is how the frequency can be measured with the help of the Weins bridge. This is the circuit diagram. In that diagram we are having the parallel combination of capacitor and resistor also, and in one arm we are having the series combination. So just like in the resonance circuit we got the frequency as 1 upon 2 pi RC, here also we are getting the same formula. Okay. So in this video we studied the measurement of frequency using the Weins bridge. We studied its circuit diagram and then we derived the equation for the frequency. So I hope that this topic is clear to you. Thank you.